Hello everyone. So in this video, I want to talk about cardinals. Cardinals are a cool class of ordinals, which we can use to assign sizes to sets. So we proved in the previous video that every set isn't bijective corresponds with an ordinal, and this will be a nice way of viewing sets because the ordinals are ordered, so we can essentially order all sets in some sense by just turning them into ordinals and then comparing them. However, some sets are in bijective correspondence with multiple ordinals, so in this situation, we want to pick like a canonical one to represent it, and we're going to choose like the smallest one, basically. Okay, so let's get down to writing it properly. So definition. So we say that an ordinal alpha is a cardinal if there is no element of alpha which is in bijective correspondence with alpha. There is no smaller ordinal, so element of alpha, alpha prime, such that there is a bijection phi from alpha to alpha prime. Okay, so it's an ordinal such that I can't make it smaller without dropping the ability to biject between things. And all our favorite finite numbers will be cardinals in the situation. If I have three things and I get rid of one, I can't match the two things I have left in one-to-one correspondence with the three things I had at the start, and this generalizes that idea. But there are some infinite ordinals which are not cardinals, which we'll get to in a later session. Okay, so I have a notion of cardinal. I claim this is sort of describe the size of sets. So I need to tell you how to take a set and give it a cardinal. So definition. If X is a set, then we define X cardinality to be the unique cardinal such that there is a bijection phi x from x to x cardinality. So this definition has a claim in it, essentially. I'm claiming that there is a unique cardinal and biject corresponds with x, and this is not too hard to show. So I need to prove this definition. I prove it's well defined. So proof of well definedness. So if x is a set, we proved in the previous video that it's in bijective corresponds with an ordinal. So x uh, there is some ordinal alpha such that there's a bijection from x to alpha. There is a bijection, say psi x from x to alpha. Okay, if alpha is a cardinal, we're already done. So if alpha is a cardinal, then we have it's in bijective correspondence with a cardinal. We are good. Uh, you might be wondering, well, why is it not in bijective correspondence with two cardinals? Well, if it's in bijective correspondence with two cardinals, then one of the cardinals is larger than the other one. And by composing the two bijections, we get a bijection from the larger cardinal to a smaller cardinal, which is impossible because that means the larger cardinal is not a cardinal because it's in bijective correspondence with a smaller ordinal. Okay, so if this is a cardinal, we're already done. And essentially, we're just trying to show that it's in bijective correspondence with some cardinal. Okay, so If alpha is not a cardinal, then that means it's in bijective correspondence with a smaller ordinal. So there is alpha prime in alpha such that there is a bijection from alpha prime to alpha. So I can look at the set of things in alpha, which are the same size as alpha in the sense that there's a bijection between them. So this is a non-empty set. So alpha prime in alpha such that there exists a phi from alpha to alpha prime, or I guess alpha prime to alpha the way I did it. Although you can always invert a bijection to get another bijection the other way around, uh, which is which is a bijection. So where phi is a bijection. This is a non-empty set. It exists by the axiom of specification, and it's non-empty because of the comments above. This is non-empty. Empty. And because this is a non-empty set of ordinals, it has the smallest element. So it has a smallest element, which I'll call like beta. And this smallest element is a cardinal because it's not in bijective correspondence with any smaller one. There's nothing smaller than beta, which is in the same size as, which is for which there's a bijection from that thing to beta. Because if there were, it would be in this set, and beta is the smallest thing in this set. Because we can compose bijection to get a bijection. This beta is a cardinal, and by the definition of beta, it's in bijective correspondence with alpha. And there is a bijection from beta to alpha, and hence there is a bijection from beta to x. Because there's a bijection between alpha and x. So now I have a cardinal and a bijection from x to the cardinal, which is good enough based on the previous comments. If I have two cardinals and bijective correspondence with x, then there's a bijection between them, and which contradicts the larger one being a cardinal. Okay, so now I have that this is well defined. So for every set, I have this thing, which is the cardinality of that set, which is the unique cardinal in bijective correspondence with that set. Okay, so now we have sizes of sets. And the sizes of sets are cardinals, and cardinals are ordinals, and ordinals are ordered. So we can order sets essentially by saying which one has a larger cardinality. So uh, mark if x and y are sets, then we can say x is smaller than y if there is a if the cardinality of x is less than the cardinality of y. These are both well defined and they are orders in some way. So the cardinality of x is an ordinal. The cardinality of y is an ordinal. One of them is bigger unless it's the same, and that's that'd be the case that x and y have the same cardinality. Okay, so we have a notion of ordering sets. This order is kind of unsatisfying the way it currently is because if I have two sets in the wild, which I encounter, it's not very clear how I would be able to tell which of them is larger if either like because like one of them has to be like larger than or equal to the other one based on the order of the ordinals. But like, how do I know which way around it is? Like I've done this construction where I've shown that every set bijects to a cardinal, but this doesn't give you any way of explaining how to construct the bijection or anything. So this is not hugely practical. So I want to give a more sort of helpful way of describing this relation. I opened with this description so that you know it's well defined and that you know that you can order the cardinalities of things and whatnot. But there's a more sort of useful way of checking when this is true. So here is a theorem. There are equivalent ways of describing when sets are larger than other ones. So the following are equivalents. For sets x and y. So one, the cardinality of x is less than or equal to the cardinality of y. This is the one from before. And we can describe this by just defining nice functions between x and y. And this will be more practical, although less useful in some situations. And the theory is much richer when you talk about the cardinals as objects in and of themselves. So two, um, this one is a bit weird because the empty set gets a bit in the way for this formulation, but it's not too bad. So either x is empty or there is a surjective function f from y to x. So I can fill up all of x using y, except in the annoying case when x is empty, in which case I don't need to fill it up because there's nothing to put y into. But the empty set is smaller than all other sets. And if x is not empty, then we can check it if it's smaller than y by just trying to find a way of filling it up using the elements of y. And by filling it up, I formally mean there's a projection from y to x. And there's another way for doing this, which goes the other way around. So this is there is an injective function f from x to y. And this time we don't need to worry about the empty set. We can have an injective function from the empty set, and that's fine. So this is a useful way of characterizing when things are bigger than each other things. All of these are used very commonly in mathematics. Okay, and this is a good example of an equivalence proof. So I want to prove that a bunch of things are equivalent, and I've listed them in a sequence. So the standard trick for doing this is I show that 1 implies 2, and then 2 implies 3, and then 3 implies 1. And once I've done that, I'll know, for example, that 1 implies 3, because you can prove from 1, 2, and then prove from 2, 3, so you'll prove 3 from 1. And similarly, all ways of going between them will be equivalent if we can just do like one path through them all. So, yeah, I need to prove this for you. So we first prove that 1 implies 3. 1 implies 2, sorry. 1 implies 2. Okay, so if the cardinality of x is less than or equal to the cardinality of y, I want to conclude that either x is empty or there is a surjective function from y to x. So, assume the cardinality of x is less than or equal to the cardinality of y. Okay, and I want to show that either x is empty or there's a surjection. So I want to prove an or. So I'll suppose the first thing is false and show the second one is true. So we can conclude that at least one of them must be true. So also assume that x is not the empty set. And then we show that there is a surjective function which I'll call g from y to x. Okay, so how do I construct g? Well, I'm going to sort of copy g over to the cardinals first. So I know that the cardinality of x is in bijective correspondence with x. So first note there is a bijection it's phi x from x to the cardinality of x, and a bijection phi y to the cardinality of y. And essentially because we can apply bijections between these things, we can think of them as sort of the same thing when we're doing our argument. So showing that there's a surjection from y to x will essentially be equivalent to showing there's a surjection from the cardinality of y to the cardinality of x. And we'll get to that at the end of the proof. But for now, we'll show there's a surjection from the cardinality of y to the cardinality of x, which will be good enough because we can just apply these bijections to it at the end. So we will construct a surjection from the cardinality of y to the cardinality of x. So let's say g prime from the cardinality of y to the cardinality of x be defined by, so this is a function, so I just need to tell you what it does to everything in its domain. It's a binary relation which associates everything in the cardinality of y with a unique thing in the cardinality of x. So g prime oops, of little y, this is an element of the cardinality of y, is equal to, and there's two cases, I'll map it to just itself if y is in the cardinality of x. And if it's not, I'm going to map it to the empty set. Okay, so first we need to check this makes sense. So if y is in the cardinality of x, which is possible because like, y is just like an ordinal, it could be in there. If it's in there, I'm just going to map it to itself, and then I'll have assigned y to an element of the cardinality of x, which makes sense. And if y is not in the cardinality of x, I want to assign it to the empty set. And does this make sense? For this to make sense, I would need the empty set to be an element of the cardinality of x. How do I know that's true? Well, I know that's true because there's a bijection from the cardinality of x to x, which means the cardinality of x is not empty. If the cardinality of x was empty, there would be no surjection from it to x because x is not empty. Did I say that right? If the cardinality of x is empty, then there's no surjection from it to x because x is not empty. So I know the cardinality of x is a non-empty ordinal, and so it has the empty set in it. So this is a well-defined function. So note here I'm using x is not empty for this to make sense. Okay. And moreover, g prime is a surjective function because for every element of the cardinality of x, it's in the cardinality of y by assertion, which means it's just mapped to by itself. So note g prime is a surjection. Note for all x in the cardinality of x, I have the x is in the domain of g prime and it just maps it to itself. So g prime is a surjection. It's a surjective function. Okay, and then I can use composite shenanigans to get a surjective function from y to x. So I'm going to do first phi y, and then I'm going to do g prime, and then I'm going to do phi x inverse. Recall that phi x inverse is the binary relation obtained by reversing all the tuples in phi x. So here phi x inverse is defined to be equal to, let's say, z x such that x z is in phi x. And because phi x is a bijection, this is also a bijection. This is a routine exercise. Okay, I'm going to pose these three things. This is a function. It starts at y, it goes to the cardinality of y, and then it goes from the cardinality of y to the cardinality of x, and it goes to back to x. So from y to x, and it's a surjective function because it's a composite of surjective functions. Everything in x is the image of something in phi x inverse. Each of those things is the image of something in g prime, and each of those things is the image of something in phi y. So here, and moreover, this function is surjective. This function is surjective. Okay. So I have a surjective function, which is what I wanted. So I've proved that 1 implies 2. The next one is 2 implies 3. So I need to show that if I have an empty set or a surjection from y to x, then there's an injection from x to y. So want to show that if x equals empty or there is a surjective function g from y to x, then there is an injective function f from x to y. So how do I do this? Well, I need to show that each of these two cases implies that. So if x is the empty set, and this is not too bad, I can use the empty function. Then the empty set is a function from x to y. It's a set of tuples where the first entry is in x and the second one is in y. So here, this empty set, this thing which looks like a phi is actually the empty set. So I'm not like mixing notation. So phi maps, the empty set maps from x to y, and this is an injective function. It doesn't send two different things of the same thing. There are no two different things at all. So it is an injective function from x to y. Okay, so the other case, if there is a surjective function, g from y to x, then I want to conclude there's an injective function from x to y, and I can do this as so. So I'm going to use the axiom of choice here. I'm going to define a choice function on the power set of y without the empty set. Then let c from the power set of y without the empty set. So this is to y be a choice function. So this is a function which takes every non-empty subset of y and just picks one of its elements. And I can uh, do this thing where I just sort of pick a thing in the pre-image of each element of x, and it will give me a function. So a sort of side note, it's a useful notation. If I have a binary relation, if say B is a binary relation from, in this case, the one I'm going to do is from x to y, then if x is in x, we define x b, even if b is not a function, we define it to be the set of all things related to x by b, y and y such that x, y is in b. This almost agrees with the notion for when b is a function, except when b is a function, we look at this as like so if b is a binary relation, which is not a function, this gives me a set of things in y. If b happens to be a function, then this case would give me a singleton in y, and this singleton is the singleton which is usually denoted xb, and we determine which one we mean from context. But I will now apply this to a non-function, so it's useful to be familiar with this. The non-function I'll apply it to is the inverse of a function, is the inverse of g. So yeah, so for all, so we now defined f, we define f from x to y by f applied to x is equal to, I take x, I do g inverse. So g inverse is the inverse of a function. It's the inverse of a binary relation. So I just swap all the pairs in g. I get a binary relation. So here gx inverse, xg inverse is the set of all things in y which g maps to x. So that's the set. And I can apply my choice function to it. And this is a well-defined definition. This is a non-empty subset of y. It's non-empty because g was surjective. And I've chosen a thing from it, which is in y. So I've mapped x to a thing in y. I claim that f is injective. Oh, I just need to show that if I have two different things, then their images are different. So if uh, x naught is not equal to x1, then x naught f g is equal to x naught because I know that my choice function just picks a thing which g maps to x naught for my x naught f. So g just undoes the g inverse there. And I know that x1 f g is equal to x1. And I know that x naught f g is equal to x1 f g. Sorry, this is not equal to x1 f g because I just said that they were equal to x naught and x1 respectively, which means that x naught f is not equal to x naught x1 f because if it were, these would be so x naught f is not equal to x1 f. So I took two different things and I showed they're not mapped to the same point. So f is injective, and that's the next part. So there's one part left, which is sort of the hardest part. So finally, I need to show that 3 implies 1. I need to show that if I have an injective function from x to y, then the cardinality of x is less than the cardinality of y. Okay, so now I'm going to suppose that f from x to y is injective. I'm going to use the same trick I used before to sort of copy this over to the cardinals. So by composing with appropriate bijections on each side, we can thus find an injective function let's call it f prime from the cardinality of x to the cardinality of y. Okay, and I want to conclude that the cardinality of x is less than the cardinality of y. Okay, so the idea is going to be we're going to look at the image of this function. So the set of points we can get by applying this function to things, and that's going to be our sort of real stepping stone for showing that the cardinality of x is less than the cardinality of y. So let's say I be defined to be equal to the image of f prime, which is just generally meaning y in y cardinal such that there exists x in x cardinal with x f prime equals y. So it's the things we can get by applying f prime to stuff. And note that I is well ordered because I is a subset of y with the cardinality of y. So note I is well ordered because it's a set of ordinals. Okay, so if it might be the case that I just isn't ordinal. If I was an ordinal, it would follow that I is greater than or equal to the cardinality of x because it's in bijective correspondence with the cardinality of x. And it would also be less than the cardinality of y because it's literally a subset of it. And that's, it means it must either be equal to it or be an element of it based on how ordinals work. So the idea is going to be we're going to modify I a bit to turn it into an ordinal, and then we'll be done. Okay. So I have a claim which I'm going to use to turn I into an ordinal. So claim if alpha is an I, then there is a unique ordinal we'll call alpha star, which is less than or equal to alpha, and I'll write it like this. There's a unique ordinal alpha star and a unique bijection, say phi alpha from alpha to alpha star, such that this is an order isomorphism, it preserves order. So for all beta, gamma, and alpha, beta is less than or equal to gamma if and only if uh, beta phi alpha is less than or equal to gamma phi alpha. So there is a unique ordinal which is order isomorphic to this thing. And moreover, this ordinal is less than alpha. So moreover, uh, alpha star is less than or equal to alpha. Okay, and this is going to give me my way of turning I into an ordinal. I just turn all its elements into ordinals, basically, and then we take the limit, as it were. We'll formalize this in the proof. So proof of clear. Well, if this is false, then this is the smallest thing for which it's false, because I is well ordered. So if this is false, then there is a smallest alpha in I uh, for which this is false. Okay, so now I can attempt to extend the thing and reach a contradiction. So either alpha is the has a largest element or it doesn't. So if alpha is equal to say uh, delta plus, then we know that delta, I know then phi delta is a thing which is well defined, is from delta to delta star is defined. And I can just extend it to a new thing. And we can extend phi delta to phi alpha by mapping alpha to the smallest ordinal, which is larger than everything in the image of delta, so larger than delta prime. By mapping alpha to the smallest ordinal, which is not in delta prime, or delta star, which amusingly is equal to delta star. So phi alpha defined to be equal to phi delta union map alpha to delta star is an order isomorphism from alpha to an ordinal. It's the successor of delta star. It's an order isomorphism in the sense of given the claim. So isomorphism from alpha to delta star plus and uh, alpha is larger than or equal to delta star plus because alpha is greater than or equal to delta. And alpha is greater than or equal to delta star plus. So this is a contradiction. So if alpha is not the successor of a thing, if alpha is not a successor, so that means every element of alpha has a successor in alpha, is not the successor of another ordinal, and ordinal, then every element of alpha has a larger element in alpha which contains it, then alpha is equal to the union of alpha. So I can just take the union of the maps. So we can define phi alpha to be equal to the union for, say, delta and alpha of phi delta. And this is a map to an ordinal because it's the image of all these things are ordinals, and we're just taking the union of them all. The union of ordinals is an ordinal, and it's an order isomorphism because it has to like the restriction to each of these things have to agree because they're each order isomorphisms to ordinals, and I claimed it was unique in the claim. So this is a well-defined function, and this function is well defined, and it gives me the ordinal output is less than or equal to alpha, because if it was larger than alpha, then there would be elements of alpha which maps to like alpha, which is a contradiction because it doesn't map to anything bigger than it. And this satisfies the claim. Also, anything which satisfies the claim has to be equal to this because it has to agree with this on its restrictions that all the elements of alpha, because each element of alpha only has one, such order isomorphism as described in the claim. Okay, so now we've got the claim. So for each alpha, there's a unique ordinal corresponding to it, which is less than is, and we have an order isomorphism. Okay, so by the same idea in the proof of the claim, so we can then take the union of these. So we can then define phi I from I to some ordinal, which I'll call alpha I, uh, by phi I equals the union for alpha in I of, it's phi alpha. And then alpha I is an ordinal, and alpha I is an ordinal, and every element of alpha I is less than one of the elements of I. Moreover, every element of alpha I is less than an element of I. Okay, so alpha I is my ordinal, and I have a bijection to it, and I know that everything in alpha I is less than the thing in I. So I now have a bijection from X to alpha I. So there is a bijection by composing the previous two bijections. There is a bijection, which I'll call like phi xi from cardinality of X to alpha I. And alpha I is an ordinal. Moreover, even though it's an ordinal, it's every element of alpha I is less than an element of I. And every element of alpha I is less than an element of I, so which means alpha I is a subset of the union of I, which is a subset of the cardinality of Y, because I is a subset of the cardinality of Y, and Y is like transitive. So the cardinality of X is less than or equal to alpha I, because alpha I is an ordinal in bijective correspondence with the cardinality of X, and the cardinality of X is a cardinal. And this is less than or equal to the cardinality of Y, because it's an ordinal and it's a subset of the cardinality of Y. So we're done. We've concluded that the cardinality of X is less than or equal to the cardinality of Y. Okay, and that was the hard part. So we now have the cardinals work and compare the way that we want them to work, which will be very useful in future endeavors. The last thing I want to talk about in this video is establish that cardinals get like really big. So we've shown in the previous video that ordinals form a proper class, and it's not the case that the ordinals just sort of stop being cardinals at some point and then keep being ordinals forever. The cardinals also keep going forever in the same sense, and we will formalize this. So the first thing I want to do is show that for any set, there's like a bigger set, so that like the cardinal keep going. So here's a theorem. So if X is a set, then there is a set Y with the cardinality of x is strictly less than the cardinality of y. So every set, there's a larger set. And we're going to prove this using power sets. And essentially using the same idea used in the first set ZFC axioms video, Russell's paradox. So, proof. Okay. So what's my y set? Well, my y set is going to be the power set of x. So let y be the power set of x. This is the set of all subsets of x. It exists by the axiom of the power set. And we're going to prove that this set is actually strictly larger than x. We prove that power set x is strictly larger than x in cardinality, which will be sufficient. Okay, so how do we know this? Well, suppose for a contradiction is not. So suppose for a contradiction that cardinality of x is greater than or equal to the cardinality of the power set of x. Well, by our previous theorem, this means that either the power set of x is empty, or there is a surjection from x to the power set of x. And note the power set of x is not empty. So note the power set of x for any set x contains the empty set. So the power set of x is not equal to the empty set. So by the previous theorem, there is a surjective function from x to the power set of x. There is a surjective function let's say let's call it g. That's what I like to use for surjective functions from x to the power set of x. And this is going to construct a very similar paradox to given in the previous videos. So we're going to use this function to make a contradiction. So I'm going to define a messy set. So let B be defined to be the set of things x and x such that x is not mapped into x is not an element of the set it's mapped to by g. So here xg is an element of the power set of x, and x is a thing which may or may not be in it. So this is a set. And because this is a set and g is surjective, G maps to it because G maps to all the subsets of X. So there is a little b in X with B G equals B. And I'm going to ask now, how does this make sense? Like, what is B? Is B in B or is B not in B? So if B is in B, then that means that by definition, B is not an element of BG, which is equal to B. And that's a contradiction because I just said it was. And if B is not in B, then this means by definition that B is an element of BG, which is B, which is a contradiction. So either way we get a contradiction. This statement is neither true nor false, which makes no sense. So this is a contradiction. So our original assumption that the cardinality of x was greater than or equal to the power set, the cardinality of the power set of x was false. And that completes the proof. So the power set of any set is actually larger than the set in terms of cardinality. And we can use this to prove that sets form a proper class. Okay, so theorem, so cardinals form a proper class. Theorem, there is no set which contains all the cardinals. There is no set which contains all the cardinals. So the cardinals just keep going. In the same way that the ordinals just keep going forever. Not only just like infinitely far, but like far enough that you can't fit them in a set. And we're going to sort of piggyback off the ordinal proof for this. So proof. So again, we suppose for a contradiction that we can. So suppose for a contradiction that there S is a set which contains all the cardinals. So I'm going to claim that I can construct from this a set which contains all the ordinals, which will be a contradiction. Okay. So it follows that union S is a set. Then union S is a set by the axiom of union. Uh, and I know that union S does not contain all the ordinals because there's no set containing all the ordinals. So there is an ordinal alpha contained in the union, not contained in the union of S. And this is going to be my contradiction. I'm going to show that alpha is in the union of S. I'm just going to need to show that alpha belongs to a cardinal. To reach a contradiction, we need to only show that alpha belongs to a cardinal. We need only show that alpha is an element of a cardinal. Okay. So how do I do this? Well, alpha's a set, and I just proved that for every set there's a bigger one. And here I'm trying to do bigger stuff. So let uh, say y be a set such that the cardinality of y is strictly greater than the cardinality of alpha. We next want to conclude that the cardinality of y is actually bigger than alpha itself, because then we'll have a cardinal, the cardinality of y, which contains alpha. And I want alpha to be the element of a cardinal. Okay, so we want cardinality of y to be strictly greater than alpha. So if cardinality of y were less than or equal to alpha, then it would follow there's an injective function from the cardinality of y to alpha. Then there exists f from y to alpha injective, means the identity function. So the cardinality of y is less than or equal to the cardinality of alpha, which we assumed it wasn't. This is how we constructed y, which is a contradiction. So the cardinality of y cannot be less than or equal to the cardinality of uh, it cannot be less than or equal to alpha, which means it must in fact be strictly greater than alpha, which means alpha is an element of the cardinality of y, which means it's an element of a cardinal, which means every ordinal is an element of a cardinal, which means we have a contradiction. And this concludes the proof. So we now concluded that in this video that every set has a cardinality. The cardinals are ordered in a nice way. We can check if a set is larger than a set using either injections or surjections. And that for every set, there's a larger set. And I know that the class of all cardinals is a proper class. It does not form a set. And in the next videos, we will build on these ideas further. Thank you.